Now we're ready for our final step, which is building the waypoint list. It's important to note here, it's structured differently. Because our vertex is no longer between our departure point and an arrival point, we're not going to write it between, obviously, and it's not going to be a waypoint along our track. We're not going to ever go there. So it's now, I'm writing it here above and before our departure point to show that, like we already stated, it's over here way away from us and not at all important to the route we're going to be taking. It's going to be used to calculate this route, but it's not part of it, and there's some unknown distance between the two, which is why I draw these little squiggles between it and our first point right here. So to lay out the waypoints, normally, well, what I've seen some people do is they build it as 10-degree increments off of the starting point, which is fine. It works just as fine, but I always like being able to just plug the 10 degrees into the calculator, which you need to base it off of the vertex to do. So I always operate off of 10 units of 10 away from the vertex. So what we do then is, well, we need to get to within our route here. So we need to get like multiple points more than 10 degrees over. And see, we're going from 83 to 155. So if we did 10 degrees over, we'd only be at 90 degrees. 20 more over, or 10 more over, we'd be at 100 degrees, and 110, 120, 30, whatever. So we have to go up to, well, 70 degrees over. So 70 units of 10 over would give us, what, 153, 38.6. So even that isn't far enough. So we have to go, our first waypoint will be 80 degrees from the vertex. And that would give us 163 degrees, 38.6 minutes west. Just to get to a point where we're within our route. Then our next one would be 90 degrees. So an additional 10 would give us 173 degrees, 38.6 minutes west. Then we would do another 10 to 100 degrees. But doing another 10 will now have us pass over the anti-meridian. So instead of writing 183, we have to now adjust things over. So the way this works in my head best is, well, we could write off to the side here 183 degrees, 38.6 minutes west, which is technically what it is. Cut off the 183, and we know we're 3 degrees, 38.6 minutes further past 180 degrees, 00 minutes east. So we're going into the east now. So we carry the 60, drop this to 179. So 60 minus 38.6 gives us 21.4 minutes east, and 179 minus 3 gives us 176 degrees. So then our next point would be 176 degrees, 21.4 minutes east. Having crossed the anti-meridian and the international date line, we're now in the eastern hemisphere. So we had to do just that little bit of work to adjust that 10-degree jump so that it still represents 10 degrees just on the other side. Now, would you look at that? If we were to go another 10 degrees over to 110, we would get 166, 21.4 east. But our ending point is actually only 168. So we only need this many waypoints between our starting point and our ending point to have those 10-degree increments. Remember, we're going more we're going more north than south. So there isn't that much we can break longitudinally the route up into to actually follow along it. It's just not that wide of a distance. Now we could do 5-degree increments if we wanted to be anal about it, but I don't want to do that. So we're going to stick with 10 degrees. This is another reason why these north-south great circle routes aren't that common, because, well, think about it. Every meridian is a great circle. So if you're going due north, that's already a great circle route. You're already following the full circumference of the Earth. And if you're going a great circle route that is very slightly off from due north, like that, it's just curving a little bit away, you might as well just go due north, and you're not going to be that far off. So that's another reason why, if they're almost doing due north or due south, most of the time people won't actually follow a great circle. They'll just go straight for it, or they'll go somewhere close, because the more northerly or southerly your route is, the closer you are to already approximating the great circle. It only has its largest impacts if you're going mostly east-west. Therefore, really, it's only used when you're going east-west. So, all of that is to say, we now have our longitudes of our waypoints, and we can also number them now. Here's our departure point, so this is 0. This one is 1. This one is 2, 3, and then we have 4 down here as our destination. So let's organize things a bit. Now we just need to calculate their latitudes. So we do tangent of Lx is equal to the cosine of dLOVx, which we know is either 80 degrees and then 90 degrees and then 100 degrees. And those are the only 3 we need, times the tangent of LV, which is 75.7 degrees. So now we're going to go into calculating this. Remember, we should start to approach the equator. So our first one, considering how north-south this is probably going to be a huge jump down from this far south to a little bit closer to the equator, and then a even steeper jump, and then a less steep jump once we pass. We'll pass over the equator somewhere between here. It probably won't be marked at any point. So we're going to start with cosine of 80 times the tangent of A, because we have it marked as A, gives us 0.68. Oh, so we're already basically there. Remember, 0.68, I'll write this here, Lx1 equals 0.68. That is the latitude of our first waypoint in degrees. But our degrees are 0, meaning we're basically at the equator. So this could be rewritten. Remember, you just subtract the ones place, which is already empty, multiply by 60, you get 40.9. So our first waypoint is 0 degrees, 40.9 minutes south. Well, now this is the problem that I don't, I've never quite gotten a good solution to, because I'm not certain of a means by which we could determine if this is south or north. Because we basically just jumped from here all the way to either right here or right there. And it really barely makes a difference which one we pick. I'm going to say to stick to the conservative side that we already went so far that we're probably on the south end. Let's see if we can go a little further and if this will like elucidate things. So then our next, we're going to leave this unsigned. Our next one is going to be cosine of 90 times the tangent of A. 0. Oh wait, yeah, cosine of 90. Yes. See, that perfectly cleared things up for me. What is the cosine of 90? It is 0. Because if you go 90 degrees of longitude away from your vertex, you hit the equator. You have to hit the equator. Because 90 degrees, let me write it right over here. Because if this is the top of a sine wave, and that's the x-axis, 90 degrees from the top has to hit 0, exactly 0. Meaning 90 degrees from the vertex would have to hit exactly at the equator. Meaning, I think I actually must have done something wrong with this first one. Cosine of 80 should be substantially removed. Tangent of A. It's possible I did something wrong here. Because by that logic, this would be the steepest portion of the curve, which would get you somewhere back here. So there should be a pretty decent number of degrees apart from one another. Let's plug in 100 to see if that clears things up again. Cosine of 100. We know that we have to be in the north now. Times tangent of A gives us, yeah, see, negative. Oh. And it's the exact opposite amount. Because if you think about it, 10 degrees this way is still basically, it's the same magnitude from the equator as 10 degrees in the other direction. So it comes out to the same amount. Now, it's possible that I screwed up a small portion of the math before. It's also possible that no, it's not possible. There's no way that 40.9 north would be right. Well, whatever I got wrong doesn't principally change the point that as you approach the equator, you will drop off steeply. You can see there was a huge change in latitude for a very minor change in longitude, because you're already might as well be going due north in the first place. And it got you really close to the equator. There might be an issue with the math here. It might also be correct. I mean, I don't know, something's at play here. However, once you plug in the 90 value, you will get 0, because cosine times 90 equals 0. So that will be the answer for that part of the question. And then the next one over will be the same latitude as the previous one before that, just flipped into the next hemisphere. So now it's in the north, which is why the answer came out as negative in the calculator. I mean, if I did times 60, I'll get the exact same value, just negative. And then that will allow you to continue your way back towards the destination. Now, I apologize for whatever happened with these two. However, the math still stands and all of these principles still work. Like I said, this is the worst type of great circle you could ever get. Everything about this problem was designed to make it as difficult as possible. And clearly it tripped me up somewhere. But these still work. You just need to apply the exceptions that I applied to follow the system along, and you will get the right answer. You will get the waypoint list that actually works to take you to your destination, even if, as we said, this is not a realistic route because it might as well just be north-south anyway.